Okay, so let's just talk about these situations and what would happen. So if we double the number of molecules, what's going to happen to the pressure? 1 atmosphere, again, atmosphere is the pressure unit. So what's going to happen to the pressure? It's going to go up. It's actually going to double. If we double the total numbers of molecules, the whole thing's going to double. So here's an example picture. Beautiful, 2 atm. Just by putting air molecules in with a bike pump. Okay? As you remove molecules from the container, it's going to go down. Yep. And you could just keep removing it to the point that it equalizes with the outside pressure, which we've already talked about. Molecules naturally go from high to low. Just like when you have temperature changes, like with the liquid nitrogen, energy goes from high to low. It always goes from high energy to low energy. Pressure does the same thing. High pressure to low pressure. Just like with the Metrodome example we talked about. So we're adding pressure. You add pressure so much that if you put in too many molecules into a sealed container, you can blow the top off. Just like you saw yesterday with the time warp video with liquid nitrogen in a 2-liter bottle, it gets so much pressure, it just becomes too much in an enclosed container, it can blow it up. Tron?
Metrodome is like higher pressure than other places. Does that mean there's like more oxygen in there?
A little bit. Yep, because it's just air. It's not like a different mixture. A little bit more air, oxygen in Metrodome. Yep. I think they thought that we were pumping in music while the other team was doing things, but I don't know about other unfair advantage with the pressure. To make it louder, like when they're trying to call plays, they pump in music in addition to the crowd. That's what I don't know if that's ever true. Can't do that. Okay. Moving on. So decreasing the pressure is going to just decrease the amount of kilopascals. You had another pressure unit. So you just let some of them out, just like we do with the vacuum pumps, which we'll do in a little bit. Barometers. Barometers, when I was at Albany, we had one of these still. Just a couple of years ago at St. Cloud State, I saw it. I don't know if they still have it there somewhere. But they were made with mercury. And what it looked like, I'm going to go back. And they're about 1.6 meters long, as far as the size. But there's a pool of mercury at the bottom. Mercury. There's a pool of mercury at the bottom, not really a good color. I think it is more on my screen. My projector is not giving it very good color. But then there is mercury all the way up the tube. If there's a lot of pressure here, or the amount of pressure coming from the air will push on that pool of mercury and then push the mercury up the tube. So if you ever wondered where this unit, millimeters of mercury, comes from, this is where it comes from. Millimeters is the height difference here between the pool and the top in the barometer. Millimeters of mercury. If there's less air pushing on the pool, there's less air, it's not going to push it up the column as much. Say it's here. Well, now it's like 700 millimeters of mercury. Or if there's more air pressure, it'll push it up further. Now we have a higher pressure unit in millimeters of mercury. If you ever watch the news for weather, it gives you the pressure in inches of mercury. Just another unit converted from millimeters to inches. Here's a good question. Chet has a question that says, can you use anything more on mercury? He leads me right into my next slide. So, because mercury's density is so much larger than water, about 13.5 times larger than water, if you wanted to use water in a barometer, it'd have to be 34 feet high, which is not very practical. So, that's why mercury is used as a common liquid that's very dense. It could be used at room temperature, whereas there's not too many liquids that are that dense at room temperature. Ben Maurer. Where do I find it? It's in rocks, and then they separate. It's in compounds and rocks, and they separate it just like other metals. What's that? Just like they found other things. Yep. Iron and everything else. Just about all the metals, they're in compounds. You need to separate them out. All right. So here's an example of what those barometers would look like if you were just at sea level. Sea level, normal pressure is 760, as you see here. There's a certain amount of molecules from the atmosphere pushing on it. At Mount Everest, where you'd be much higher, there's less molecules pushing, so the distance that would push the mercury up would be much smaller, 253. So Large difference with different amount of pressure pushing on it. Now, we talked about vapor pressure yesterday. This is just a little picture quick of how vapor pressure is even measured. All right? We have mercury in a tube, a J tube these things are called. We got mercury, and it's equal on both sides because there's atmospheric pressure here, there's atmospheric pressure here. Then they attach these two, like you see here. And then you put some sort of liquid into this flask and see how much pressure is formed from the liquid. If there's a lot of pressure, it'll push this mercury down a lot. If there's not much pressure, it won't push the mercury down much. And this difference in height is called the vapor pressure. If you increase the temperature, more of this vapor is going to turn into a gas, and it's going to push the mercury down further. So that's how you'd measure vapor pressure in the first place, to see how much the liquid evaporated and pushed on the mercury. That's what we talked about a little bit yesterday. Okay, if you're on Mount Everest, your pressure is a lot lower. It's actually right around here for kilopascals. So we talked about yesterday how we can mess with the boiling point. The boiling point will be about 70 degrees Celsius on the top of Mount Everest. So you'd have to cook things very long if you want to cook food, but you'd get it to boil much faster because you have that low pressure. Could use a microwave? Sure, because a microwave is just going to excite the water molecules and increase the temperature. It has nothing to do with boiling. So yes, microwaving would work unless you're just depending on the boiling to cook something with the microwave, then it's not going to cook as well. But microwaves excite water molecules to make them move faster to increase the temperature. So if it's not a boiling situation, microwaves would work better. Yep. When you get to the top of Mount Everest, just find that 3-prong outlet, plug in your microwave, and go. This is another example of the setup where you have gas pushing down. Here's mercury in this tube, and a certain amount of vapor pressure formed. Okay. Water vapor, water pressure. We talked about yesterday with the water towers, how you have a certain height creates more pressure, and you can see that here with water. Well, the same thing happens with air. The higher you're up, the more the column of air above you. So Erin was talking about yesterday how she had water pressure. If she went further down into the water, there'd be even more pressure. Well, if I'm standing here versus on top of the mountain, here's a guy, here's a guy. There's a certain column of air here for the pressure. Here there's less of a column of air overall, so there's less pressure pushing down on him. Same thing with water. As you go further down, there's more pressure, so that would make this hole here push the water out further, and here not as much. Lots of stuff together. Here's where you're going to start jotting down some formulas and stuff. So this is all about gas laws. We're going to go through the variables that you need to use to use the gas laws and how they work. And go through a couple different gas laws. I'll show you some demos afterwards, and then do a practice problem with you at the end for the homework that you're working on. It's all about gas laws. So the first thing we're going to start talking about is what units need to be used to even use the gas laws. So back in 9th grade, maybe even before that, you did gas laws. Boyles, Charles, I don't know how much, if you went to the combined gas, they've kind of switched it a little bit over the years. So he definitely did Boyles and Charles laws and put them into equations, but it was a couple of years ago. We'll definitely review it. First thing first, temperature has to be in kelvins, not degrees Celsius, not degrees Fahrenheit. Why is kelvins used so much in science and formulas? No negatives. Yep, only positives. 0 degrees Kelvin, or 0 kelvins, is absolute zero. Everything above that is a positive number. So right now, 20 degrees Celsius about in here. If we want to calculate the Kelvin, we would take 20 plus 273. 20 plus 273, and we would have 293 kelvins in here right now. Not that it's that important, but kelvins is not in degrees. They're just called kelvins. Whereas Celsius and Fahrenheit are called degrees Celsius or degrees Fahrenheit. 293 is just 293 kelvins. Just a little difference in terminology. So you need to be able to convert back and forth. Will you get these formulas? Sure. They're even on the AP Chemistry formula sheet. You'll get formulas. You have to be able to use them. Kelvins, kelvins, kel, kelvins, That's an E sound, right? All right. Pressure. Pressure must be consistent. So temperature must be in kelvins. Pressure must be consistent. It needs to be in the same unit from one side to the other. So with these formulas, we're going to have a pressure 1 and a pressure 2. As long as the units are the same for both, you're fine. If they're not the same, you're going to have to convert one to the other. So once you jot these things down, go to page 364 in your book. 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 And take out the worksheet you did for today, and we'll do number 2 together. Number 2 together. So page 364, number 2 together. I'm going to star the 2 that we'll see the most in this class. Atmospheres and millimeters of mercury. Everyday life, you're going to see PSIs the most in your life. Because if you're going to buy an air gun or a air compressor from Menards, it's going to be in PSI. If you're going to buy a nail gun, it's going to talk about PSI. So PSIs are what you're going to see. If you go to look on your bike tire to see what pressure it's supposed to be pumped up to, it's going to say PSIs. But in science, atmospheres and millimeters of mercury are the most used. So on the bottom of page 364 is a chart that you will have access to, but you need to be able to use it. You'll get these conversions on quizzes and tests, but you have to be able to use them. 364. 364. So if you take out that worksheet you did for today, number 2 on the worksheet you did for today says rank the following pressures in increasing order. And then the numbers on there. A is 50 kilopascals. B is 2 atmospheres. C is 76 torr. And D is 100 newtons per meter squared. Okay? So how in the world could I compare those things? What do I need to do? Callie says I need to convert them all into one. Does it matter which one? It doesn't at all. I can convert them into any one of those units just as long as they're all converted to the same thing. So I can compare numbers. Let's just keep A in kilopascals just because it's already in kilopascals. And we'll change the other ones. So we can use dimensional analysis just like we have in the past to change these. So I have 2 atmospheres. If I want to know how many kilopascals in 2 atmospheres, I need to look on page 364. Whoops. I want to change that to a 1. 1 atmosphere has how many kilopascals? What is it, Eric? 101.325. Everyone see that? On page 364, there's a chart that says 1 atmosphere equals 101.325. So essentially, it's about 202 kilopascals. I'm not going to worry too much about our exactness right now, but it's about 202. Approximately 202. I'm just ranking right now. How about torr? How many? So I'm going to go 76 torr. And what do I know for a conversion on that chart on page 364 for torr compared to kilopascals? 1 torr equals 1 millimeter of mercury, which isn't too helpful right now. Which is also true, but that doesn't help me right now for this. So 760 torr, you're right. Everything on page 364, it says 1 atmosphere equals this, equals this, equals this, equals this. So 760 torr is also equal to 101.325 kilopascals. If I look at this, the 76 is going to cross out with the 760 and put a 10 here. So it's essentially 101 divided by 10, which is essentially 10 kilopascals. So this is approximately 10 kilopascals. You have to be able to convert from one unit to the other. You'll get this chart, but you have to be able to use it. If I want to do letter C, Or sorry, I've already done that. Letter D, 100 newtons per meter squared. Do we know any conversions between newtons per meter squared and pascals or kilopascals? Yeah, 1 newton per meter squared is equal to 1 pascal. Whoa, but that doesn't help us. We need kilopascals. How many pascals are there in a kilopascal? Yeah, if I ask the same question, how many meters in a kilometer, how many grams in a kilogram, it's always 1,000. So it's 1,001. So I look at this, I'm essentially taking 100 divided by 1,000, which gives me 0.1 kilopascals. So D is equivalent to 0.1 kilopascals. So if I want to rank these in increasing order, what is my lowest pressure, Aaron McDougall? D. So D would be my first one. What is next, Ben Marine? C. Then what, Natalie? And then B is last, with the highest of 202 kilopascals. All right? So you need to be able to convert from one to the other. You'll get that chart. Dimensional analysis works slick. Some people like to use proportions and just setting up the equation, cross multiplying and dividing. That's your deal. Go for it, but you have to be able to convert. I don't care which method you use. Moving on. Volume also must be consistent. We're going to use metric. Milliliters or liters. No bushels or ounces or quarts or teaspoons. We're using milliliters or liters. No bushels. I don't know how many quarts there are in a bushel. Offhand. But it needs to be consistent. So if I have a V1 in milliliters, V2 needs to be milliliters. Same thing with liters. Let's talk about gas laws. Oh. Okay, so there's 4 gas laws we're going to jot down, formulas for and discuss. Boyle's. Boyle's law. Pressure, volume. Boyle was the vice president, VP. You do need to know whose is whose. Volume, pressure. Boyle's law. Vice president, VP. That's assuming temperature is constant. We're going to graph this. What do we talk about? If you guys are gas molecules and I decrease the volume of the room, what's going to happen with your collisions on the wall? If I decrease the volume, what happens to the pressure? More pressure. If I increase the volume, the pressure will go down. They're inversely proportional. And a graph of inversely proportional variables looks like this. So high pressure means low volume. High volume means low pressure. With all of these formulas, you can use cross multiplying and dividing. I could give you original pressure, original volume, new volume, and say, what's the new pressure? This is a very common type of problem in Chapter 11. I would take P1 times V1 divided by V2, and I'd have solve for P2. Cross multiplying and dividing is just perfectly fine and works slick in this chapter. We'll practice that in a little bit. Here's some beautiful pictures. If you put more pressure on a piston of air, pushing down, it's going to take up less volume. Increase the pressure, decrease the volume. If I double the pressure, I cut the volume in half. So here's the graph and some data that goes with that graph. Moving on. Charles' law. Charles' law is relating temperature and pressure. This is assuming the pressure is constant. Classic example of this was the 2-liter bottle in liquid nitrogen, or a balloon in liquid nitrogen. We didn't bring one though. What happens to the volume when you decrease the temperature of a gas? What happens to your basketballs at your garage in the wintertime? What's that, Molly? They get bigger or smaller in the winter? Basketball. What's that? Smaller. So these guys are directly proportional. Temperature goes up, volume goes up. Temperature goes down in the wintertime, the volume goes down. So they're directly proportional. That's a straight line, if you can't tell. It's supposed to be. Oh boy, I did it again. It's the same exact. Wow. Just keep going and following the same thing. I know there is, but I should be able to do this. I don't want to draw a line function. It's not that important. Yeah, they switch because they're inverses. Now in a direct proportion, they will not switch. It'll be 1s over 2s and 1s over 2s. Good observation. Okay, here I have pressure from the air not changing, just atmospheric pressure staying the same. I have a little piston with air inside of it. As I increase the temperature of it, it takes up a bigger volume. Again, there's the graph we just made. Gay-Lussac's law. Lussac's. Temperature, again, going up. Pressure, going up. What do you think? Directly or inversely proportional? Increase the temperature of you guys in this room. What's going to happen to the pressure? It's going to go up. So these are also directly proportional. Has a straight line also. Directly proportional. Temperature's up, pressure's up. Temperature down, pressure down. Last one? Yeah. The last one combines them all. Yep, nothing's constant. So what we call this one, when you combine them all, is called the combined gas law. Nothing's constant. Everything's changing. Actually, the only thing that would be constant in this case is numbers of molecules of gas. We'll talk about what if that changes later. So, nothing is changing, or sorry, everything's changing. Nothing is constant. That's combined gas law. You may notice that if the volume's constant, will cancel each other out. What I have left is X. If the pressure is constant, they would cancel each other out. And what I have left is Charles' law, rearranged a little bit. But it's the same, they'll end up being the same. Temperature is constant. You can't really because there's so many things. There's too many variables. If the temperature is constant, we have Boyle's law, rearranged a little bit. So this really is where they all come from. Let's talk Dalton's law real quick. We'll do a lab with Dalton's law on Friday-ish. We'll do a lab with it. But Dalton's law is just, I mean, it's a wonderful name that John Dalton has. But this is the guy who came up with the atomic theory of matter. Same guy. Has a law of partial pressure. And he just says that the pressure, like in this room right now, there's a certain amount of pressure. And it's just the addition of all the gases in here. Pressure of nitrogen, plus the pressure of oxygen, plus the pressure of carbon dioxide, plus the pressure of argon. All those pressures added up is your total pressure. Which gas in here do you think supplies the most pressure? The nitrogen, because there's a majority of nitrogen. That would supply the most pressure. All right, don't need to write it down. Same type of thing. Total pressure, a mixture of gases, equals the sum of the partial pressures of the individual gases. We'll do a lab like this. This is also in your section 1 of your book, and we'll come back to that when we do the lab. So example, what would you expect here for the total pressure? If I added all those gases together, what would I expect for the total pressure in this same size container? Yep. Just add them up, and you get 1,100. Look at that, even turns, and it becomes it. Okay? Now this is a guy standing on Earth. He's really big compared to the Earth. But we have a certain amount of pressure from oxygen, from nitrogen, from argon, from carbon dioxide, a little bit from water vapor and other gases, but those are the majority of the gases that are in our air. Add them all up, that's our total pressure. That's all that Dalton's partial law is saying. If you have gases mixed together, they all together make the pressure.